Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures on medical imaging. In this video lecture and in the few subsequent video lectures, we would discuss in detail about image enhancements. This one and maybe the next two, we would in particular would be discussing about image enhancements in the spatial domain. Then they will be followed with image enhancements in the frequency domain. What do we mean by saying image enhancement? It means you are going to improve the quality of a given image, and to this end you might be performing certain operations either in the spatial domain or in the frequency domain. This improvement in the image quality sometimes could be qualitative, which means when you see images visually, the enhancements that you have made could help you to distinguish or see the objects of your interest clearly. And some of these other enhancement techniques could be quantitative. By that I mean, in your algorithm, when you are applying these enhancement techniques that are going to improve your results. So we would be discussing both these types of enhancements techniques, and now in this and subsequent couple of lectures we would discuss about enhancements techniques in the spatial domain. When we say enhancements in the spatial domain, it means we are going to perform a direct manipulation of pixel intensities of a given image. Again, these techniques can be further divided into two categories. One we refer to as intensity transformations, and the other one we refer to as spatial filtering. When we say intensity transformation, we make these enhancements just based on individual pixel intensities, and we will not be worrying about what are the intensity values of its surrounding pixels. In other words, intensity transforms operate at a single pixel level. On the other hand, when we discuss about spatial filtering, in order to identify the new intensity value for a given pixel for enhancing the quality of the image, we would be looking at the neighborhood of each pixel as well. We will discuss them in more detail and it becomes clear to you as we move on. One more point before we go in details about the spatial domain enhancement techniques is, you would realize as we move on that certain enhancements are easier to perform in the spatial domain, whereas other types of enhancements would be easy to perform or effective to perform in the frequency domain. As a part of this course, we will be studying the most commonly used enhancement techniques both in the spatial domain as well as in the frequency domain. The spatial domain enhancement techniques can be explained using this diagram here. This is your image here, x and y axis. Let xy be coordinates of the pixel. Now if the intensity at that pixel is f of xy, at the end of this process you are going to find a transformation of this intensity value. F of xy is one intensity value that would give you the new intensity value to which it gets mapped to. As you could see here, this is dependent on the intensity value that you have at f of xy. If you are looking at intensity transforms, the first subcategory of spatial domain processing, that is equivalent to, still you could represent it with a neighborhood for a mathematical purpose, but then it would be having a neighborhood of 1 by 1. On the other hand, when you are looking at filtering techniques, spatial filtering techniques, this could be, let's say, 3 by 3 neighborhood, 5 by 5 neighborhood, and so on. Of course, if it is a 3D image, then you will have one more dimension, 3 by 3 by 3 neighborhood, and so on. Yeah, here we are mentioning it in terms of 2D. 1 by 1 neighborhood is what you get there are intensity transforms, with W by W neighborhood with W greater than 1 would give you spatial filtering. We would come back to the second part a little later, but what we now would be discussing would be referred to as intensity transforms. Part of these techniques are referred to as contrast enhancement techniques or contrast stretching techniques or point process techniques. And anyway, the second part we will come to it a little later. In this lecture, what we are going to discuss are four basic types of functions that are frequently used for performing intensity transformations in the spatial domain. The first one being linear transforms, where there are again two categories, negative and idea transform and identity transform. We will see them shortly. Another one, logarithmic transforms, log transform and inverse log transform. We bunch them together under this kind of transformation. Other one is power law transforms, where you might be taking nth power or nth root power. Both of them are grouped together under power law transform. And the last one being piecewise linear transform. We will see a couple of transforms under this: contrast stretching and gray level slicing. This graph is showing you some of these transforms. For example, this x-axis is input intensity values R, and to the values that it gets mapped to are given on the y-axis. For example, if we are going to take an identity transform here, you could notice here that input intensity is getting mapped to the same intensity as the output. There is essentially no change in the intensity values. Negative transform, it's a reverse mapping is happening. Input value of 0 is getting mapped to L-1 value here, and input value maximum intensity is getting mapped to an output intensity of 0. And this is showing you a logarithmic transformation. This, for example, graph would show you taking an nth root transformation. This would show you the nth power transformation. We'll come back to it. Before that, let me also take you through contrast stretching and thresholding transforms. You could see here all this range of low intensity values are mapped to 0, high intensity values are mapped to a particular maximum value beyond a particular threshold, and in between you would be stretching the values. A small band of values or range of values, input intensities are mapped to a large range of values here. That's why it is referred to as contrast stretching. We'll see it again in more detail shortly. Before that, let me just finish this off with telling you about a thresholding function, where consider a value of k here. Any value less than or equal to k is mapped to 0, and any value greater than that getting mapped to the highest intensity value, let's say L-1 there. This is referred to as a thresholding function. Now we will see each of these transforms in more detail. Identity transform, anyway, it gives you the same image, so there is nothing much to discuss there. Second type of linear transform is image negative transform. This is how the transform looks like. What we are going to do here is, for example, 0 value is mapped to L-1 value. Assume that you have L distinct intensity values, which means you are having values from including 0, you are having values from 0 to L-1. In other words, the maximum intensity you have in a given image is L-1. Now, what this negative transform is doing you is, the input intensity of 0 is getting mapped to the maximum possible intensity value, which is L-1. So if you are considering a 8-bit representation, this would be 255, and maximum intensity value, which is L-1, for example, is getting mapped to 0. So this would be the resulting equation now. R is your input intensity, S is your output intensity, L-1 is the maximum intensity that you could have in the given image. So you could clearly see here, when your input intensity is 0, it is transformed or mapped to L-1. Similarly, when your input intensity is L-1, this is getting mapped to 0. If you apply on the Einstein present on the left side, you will end up with the Einstein who is there on the right hand side. I'm sure you have seen this effect in movies, particularly when some flashback story is told, you would use a similar kind of effect. As far as the algorithm is concerned, this might not bring you quantitatively any improvement, but in certain cases, this helps you to visualize things in a more convenient way. For example, this image is showing you the mammographic image of the breast. You could notice here there is a tumor here in this region, and when you apply this negative transformation, you could notice here the tumor. It is more convenient to observe the tumor after application of this negative transform. But as I said, this might not improve the quantitatively your results, but sometimes this would help you to visually make it more convenient to take a look at the resulting images and make inferences from the resulting images. Another transform is logarithmic transform. The most common form of this transform is what you see here, s equal to c times log of 1 plus r being your input intensity value, s being the output intensity value to which you are mapping r, and you are adding 1 to r so that you will not end up with infinity, particularly when r equal to 0, and then you are scaling them as well. This effect could come, for instance, your input intensity range is different from the range of values that you would like to use in the enhanced image, so you could have accordingly a scaling value there. Also, to take into account the scaling implicitly happening because of log, you want to map it to a different range. That's what you could control with C. Let us see what this transform is doing by looking into this graph. This is your logarithmic transform here. You can notice here the values over a small range here are getting mapped to a broader range here. On the contrary, when you see very large values, they are getting mapped to a very small range of values in the output. This essentially could help you. For example, there is a broad spectrum of values are there, or a very large range of intensity values are there. You would like to simultaneously see both low values and high values, but if you use a simple linear transform, you won't be able to see or visualize the intensities of which are there on the lower end. On the contrary, because of the way you are mapping the intensities, you would be able to see so even if there is a very dominating intensity value in your image, you could still see the rest if you are applying a transformation similar to this log transform. This is an example of applying a log transform to a magnitude spectrum. Those of you who had experimented with computing the DFTs would be already familiar with these kinds of graphs. Assume that this is the image on the left hand side is a simple magnitude spectrum. Because of the high intensity value that is there at the center, you won't be able to observe the frequencies that are there or the harmonics that are there at higher values of frequencies. On the contrary, when you are applying a transform like s equal to c times log of 1 plus r, you would be able to visualize and also realize that there are indeed higher harmonics and they can be visualized here. So this is one instance where applying this transformation could be useful. Another set of very widely used transforms is gamma transformations. This is also referred to as power law transforms. The equation for this transform is as seen here. R is your input intensity. You are going to raise it to the power of gamma and then scale it with C. Since you are raising this power of R to gamma, this is referred to as gamma transformations commonly, and the output intensity is S. On the x-axis you have R, on the y-axis you have S. Assume that for the time being C equal to 1 and take gamma equal to 1 for example. So then you get a linear transform, which means S equal to R. They are mapped to the same intensity values. Notice what would happen if your gamma value is greater than 1. Then you would get graphs like this. This is gamma equal to 1. For example, this is the graph showing you the values for gamma equal to 1.5. This is 2.5, 5, 10 and 25 and so on. So what's happening here? How can you interpret these graphs? The way you could interpret them is when your gamma value is greater than 1, you could notice here even a small range of high intensity values are getting mapped to a large range of values here. On the contrary, low intensity values, a broad range of low intensity values are getting mapped to a small range of intensity values here, and this is becoming more and more dominant as you are increasing the gamma value. So if your object of interest is lying in high intensity range, and if it is not very clearly visible there, a gamma transformation could help you in getting much better contrast for those regions. On the contrary, take a look at these graphs when your gamma value is less than 1. For example, this is gamma equal to 0.67, gamma equal to 0.4, 0.2, 0.1, and so on. Now you could see that when gamma value is less than 1, the lower intensity values are getting mapped to a broad range of intensity values compared to the input range. So for example, if you are having a dark image, or your object of interest is having a low intensity values, then using this transformation with gamma value less than 1, and of course you need to figure out which gamma is better for you depending on the image, would enhance the quality of your output image. This is an example of this, where you have the MR image of the human spine. You could hardly see anything here. So here it is indeed the low intensity values that you would like to enhance, which means you need to apply gamma values which are less than 1. So this is the value that you have for gamma equal to 0.6, gamma equal to 0.4, and this one for gamma equal to 0.3. You could notice here the regions, the black regions are the dark regions where you cannot see any distinction in the original image. Now you are able to see a distinction as you are reducing the gamma value. But if you are reducing it too much, then you might end up with some artifacts which otherwise are not there in the original image. So we need to figure out the right value there, but you could see the effect of gamma correction here in enhancing the quality for your objects of interest. This is example on the other extreme, where most of the intensities are on the higher side. Even a small band of high intensity values, now you want to map it to a large range of intensity values, which means you need to take gamma values which are greater than 1. So these images are showing you the gamma values for 3, 4, and 5, how this image gets transformed to. You could now notice that the contrast is much better here, and of course when you are increasing it too high, you could also notice that this image is getting darker. So again, there is a trade-off at which you could get a very good image enhancement with the gamma correction. The next set of transforms is piecewise linear transforms, where your mapping is linear, but as the name says, it's a piecewise linear transform. You consider the graph here. You are taking this transform for, let's say, in between L by 2 and L by 4 to here. Then you are using a different scaling here and another slope here. Say for example, your object of interest might be in this range of R1 to R2, where you want to have the maximum contrast. So you are mapping here R1 and R2, you are stretching it to the maximum by making use of this piecewise linear transform, and that is when you would be getting this result. On the other hand, instead of this contrast stretching, if you are applying a simple thresholding operation, where any intensity below a particular value of, let's say, R0, you make it to 0, and any value above that you will make it to L-1, you will get a result as shown here. Two other transforms that we are going to take a look at in this video lecture are as shown here. You could notice here again, this x-axis is your input intensities and y-axis is the intensities to which you are mapping them. Unlike the thresholding, where any value higher than a particular value you are mapping it to just one intensity value, here what we are doing is, this could be a range of intensities. So any intensity between A and B will be mapped to one value, and the rest would be mapped to another value. So you could think of it as your object of interest is having intensities in between A, B values. So that's what you want to see, and the rest you want to make it 0. Then you could use a transform like this. This is another way of transform. What is happening on the transform shown here on the right hand side is, for example, it is linear till A, which means whatever is your input intensity, you keep it same in your output image. On the contrary, your object of interest being A, B, that's what you would like to see, that you will be mapping here to a single intensity value, and the rest of the intensities again from B to L-1 you keep them same. If I put the dots here connecting these 2 points, it would have been a linear transform, but now what I am doing is my object of interest, I am putting a specific intensity value here. This is an example that is showing you the application of this transformation or the importance of this transformation. This is applied to aortic angiogram and the effect of it. You have, let's say, an image shown on this left hand side. Suppose if you are applying a thresholding transformation and these are the blood vessels, assume that it's the blood vessels that you want to take a look at, and the rest you just want to merge it into the background. So that case, if you figure out the intensity range for the blood vessels and then apply a transform like this, what you would end up is seeing just these blood vessels, and then you could probably take a look into whether there are any clots there with this transform. Another transform is where the remaining are also kept in the background, and then this might also help you to visualize few other structures that are there in the background, but still being able to see the blood vessels more predominantly in the image. With that, we will wrap up this lecture, and in the next video lecture, histogram based intensity transforms we are going to discuss. Thanks for watching. See you in the next video lecture. Bye. Take care.